What you're watching is not an animation. This is our sun, firing a billion-ton cloud of plasma into space at millions of miles an hour. In July 2012, one of these, the biggest in 150 years, crossed Earth's orbit. It missed us by 9 days. 9 days? If it had hit, you wouldn't be watching this video. No internet, no power, no phones for months. Between you and that star stands exactly one shield. This is the story of the day the sky caught fire, the bullet we dodged, and the reason scientists say the next one is a matter of when, not if. To understand what almost happened, you first need to meet the monster itself, up close. The sun's surface is a boiling ocean of plasma, tangled in magnetic field lines. Sometimes those lines twist into dark knots, sunspots, each one big enough to swallow the Earth whole. When a twisted knot snaps, it releases a solar flare, a flash of energy equal to billions of hydrogen bombs going off at once, in 1 second. And sometimes the sun goes further. It tears off a piece of itself, a billion-ton cloud of magnetized plasma, and hurls it into space. Astronomers call it a coronal mass ejection. And sometimes Earth is standing in the way. Which brings us to a quiet English morning, September 1st, 1859. An amateur astronomer named Richard Carrington was doing what he did every clear day, projecting the sun through his telescope and sketching sunspots. Then, right before his eyes, 2 blinding points of white light ignited on the sun's face. He was watching the most powerful solar flare ever recorded. With his own eyes, he ran to find a witness. Within a minute, it was gone. But the bullet was already on its way. 17 hours later, the cloud slammed into Earth, twice as fast as any storm we've measured since, and the night sky caught fire. What happened over the next 2 nights sounds like fiction, except every word of it is documented. Auroras, normally locked to the poles, blazed over Cuba, Panama, and Hawaii. In the Rocky Mountains, gold miners woke up and started cooking breakfast at 1 a.m., convinced the glowing sky was dawn. And then the world's technology, all of it, which in 1859 meant the telegraph, went haywire. Sparks leapt from the wires. Operators were shocked at their keys. Telegraph paper burst into flame. The sky was running electricity through the wires. Some operators disconnected their batteries and kept sending messages anyway, powered by nothing but the storm itself. The line between Boston and Portland ran for 2 hours on pure aurora. And remember, in 1859, electricity was a novelty. The world shrugged, the sky faded, and everyone moved on. Today, that same storm would find a planet wrapped in wires. So what actually reaches us when the sun takes a shot at Earth? It comes in 2 waves. Wave 1 is the flash, light and X-rays. It arrives in just 8 minutes and jams radio signals on the daylight side of Earth. Wave 2 is the heavy one, that billion-ton plasma cloud arriving 1 to 3 days later. When the cloud hits, Earth's magnetic field takes the punch. It catches the charged particles and funnels them toward the poles. And that glowing collision is exactly what an aurora is. The northern lights are our shield, visibly straining. But a violent storm shakes that entire magnetic field. And a shaking magnetic field induces electric currents in any long wire it can find. In 1859, that meant telegraphs. Today, it means the power grid. Same physics, much bigger wires. If that sounds theoretical, ask the province of Quebec about the morning of March 13th, 1989. A solar storm slammed the grid, currents surged through transmission lines, and protective systems began tripping like dominoes. From the first alarm to total collapse took 90 seconds. 6 million people lost power. The blackout lasted 9 hours in freezing March cold. And here's the part that should get your attention. That storm was several times weaker than the Carrington event. Several times weaker. Now we get to the one they don't teach in school. July 23, 2012. That day, the sun unleashed a Carrington-class monster, possibly stronger. It tore across space at 6 million miles an hour, and it crossed the exact spot where Earth orbits. 6 million miles an hour, from sun to Earth in under a day. We know exactly how bad it was because a solar observatory called Stereo A was sitting right in its path and took the hit. Its instruments measured a storm that would have rivaled 1859. If the eruption had come 9 days earlier, Earth would have been standing exactly there. 9 days of orbital motion. That's the entire margin between an ordinary July and the biggest technological disaster in human history. We never even felt it pass. So let's ask the uncomfortable question. What happens if a Carrington-class storm hits us? Today, the storm's currents would overload the giant transformers that anchor the power grid. Here's the problem. Those transformers are custom-built, weigh hundreds of tons, and replacing one takes many months. We don't keep spares for a continent. Above our heads, satellites would tumble and fail, taking GPS, aviation routes, and communications with them. And the fleet we depend on today is 50 times larger than it was in 1859. We've never stress-tested this world. Even the internet isn't safe. The deep-sea cables that carry it between continents are fine. But the powered repeaters strung along them every 50 miles are not. One bad storm could cut continents apart for weeks. And without power, everything cascades. Water pumps, fuel pumps, banks, refrigeration. Studies put the cost in the trillions of dollars, with recovery measured not in days, but in months to years. Modern life runs on a grid the sun can switch off. Here's the good news, and there genuinely is some. This time, we're watching the sun like hawks. Observatories like SDO and SOHO track every sunspot and flare in real time. When an eruption leaves the sun, we get 1 to 3 days of warning while the cloud is in flight, enough time to prepare. And warned grid operators can fight back, rerouting power, lowering loads, shielding the most vulnerable transformers. Done right, a civilization-ending storm becomes a very bad week. In May 2024, the strongest storm in 20 years hit us. Auroras glowed as far south as Florida. The grid held. The warnings worked. It was a live test. And we passed. But that storm was still no Carrington. Which leaves one final question. The one everything else depends on. When is the next big one? Tree rings and ice cores show the sun has fired storms even bigger than Carrington in the past, long before anything electric existed to notice. Statistically, scientists put the odds of a Carrington-class hit at roughly 1 in 8 per decade. Roughly a 1 in 8 chance every 10 years. Those are not comfortable odds. It might be decades away. It might be next spring. The sun doesn't publish a schedule. The only certainty is that the bullet will fly again. But here's the thought I want to leave you with, because this isn't really a story about fear. Every gram of food you've ever eaten, every warm day, every sunrise. All of it is the same star's energy that once set telegraph wires on fire. We don't just survive the sun, we are made possible by it. 1859, 60 seconds of warning. Today, 3 days. And we've become the first generation that can actually see the bullet coming. Carrington had a sketch pad and 60 seconds of warning. We have a fleet of sentinels staring at the sun around the clock. So the next time the news says a solar storm is coming and the sky begins to glow, you'll know exactly what you're looking at. A shield, holding, and a star, reminding us who's in charge. Would we really be ready if it hit next year? Tell me what you think below. and subscribe, because the universe keeps sending warnings and we keep reading them together.